This video clip is part of the EPFL introductory course on information computing and communication. It is the second in a set of video clips on information storage and management. It briefly introduces the main types of data structures typically found in the information world. The simplest possible data structure is that of an indexed sequential catalog, such as a catalog in a library. One could of course place the books on the shelf by alphabetical order and not bother with a catalog at all. This is indeed what most people do at home or what you find in smaller bookstores. It does, however, present two drawbacks for a large institutional library. First of all, to find a given book, one may have to walk hundreds of meters of shelves to get to the desired letter and book. And secondly, every time the library would acquire a new book to be inserted in an already full shelf, one would have to shift tons of books, so to speak, towards the right to preserve the alphabetical order. It is thus much simpler to place books in chronological order of acquisition, adding new shelves and storage as needed. And at the same time, one can record the place of every book on an index card to be inserted in a catalog sorted by alphabetical order. Of course, by doing so, the searching and overflow problems just mentioned at the library level are merely transferred to the catalog level. It is, however, much simpler to solve that problem at the small scale of the catalog rather than at the large scale of the library. Indeed, sifting through and moving index cards or drawers is much simpler than sifting through and moving entire bookshelves. What is true for a book library is also true for a computerized filing system. Although it is about bits rather than books, searching and moving large files of data would imply many more accesses to disk for reading and copying files than searching and moving small indexes of just a few bytes that can all fit in a few disk records or a few memory blocks. If such an electronic index catalog simplifies the retrieval of a particular file, it does, however, not allow retrieving from a media library all the works of a given author unless one knows all of their titles. To answer such questions, one should rather use hierarchical file systems such as depicted here. In such a system, all content is organized into a tree structure. That structure is anchored in a so-called root catalog, often denoted by the slash sign in Unix or Linux systems or by the backslash character in Windows systems. Information is then classified by type, such as, for instance, programs, data, user files, etc. Under such a title as users, one then finds text documents, music, pictures, video, etc. Pushing down into the music catalog, one can then find different MP3 recordings, further sorted by author, composer, interpreter. Only the bottom level contains the actual unstructured sequential MP3 recordings. All other levels of the hierarchy build up the structured part of the information system. If such a library is much more structured than the preceding index sequential one and allows more targeted searches and more direct access, it does, however, still not allow the easy retrieval of the different executions of a given work by different artists. Answering this last question remains complicated because it does not fit the strictly hierarchical structure of classical file systems. The world of information is not strictly hierarchical, but rather multi-relational. Every piece of information, like a musical MP3 in the present example, is not associated to one single parent, but instead can be associated to a number of authors, composers, and artists. Many relational questions, such as the one asked above, can be answered easily only if they are presented to a database reflecting the desired structural relations. This is the case of the database on this slide, which structures information in tables, where each table reflects various relationships. The set of all tables taken together even allows reflecting additional relations not immediately visible in any single table. For instance, all the works composed or interpreted by a given individual, that is, two different and orthogonal hierarchical relations that are not explicit in any table but can be inferred by extraction from them. If that media library is again more structured than the preceding strictly hierarchical file system, there will always exist some more sophisticated questions that cannot be easily answered directly. For instance, this database does not allow easily finding out if a lyrics author has also composed the score and interpreted the resulting piece of music. A more general type of database, which is functionally equivalent to a relational database, is a so-called entity relationship database. This slide shows an example of such a database. First, consider a popular song of which the original version has been adapted into one or more languages. Such a song thus exists in two or more versions, linked by an adaptation or translation relationship. The different versions would typically share the same score, but each would have its own lyrics version. The score, the lyrics, and the song titles would be linked by relations as represented here. Furthermore, the score must have been written by one or more composers, while the lyrics would have been written typically by different authors, as represented here. Then again, a number of different artists may have sung the different lyrics on the same score, as shown here. An entity relationship database would maintain all the structural information separately from the actual recordings by the different artists. While the structural information is syntactically and semantically rich, it represents only a fraction of the volume of the database. It can thus be moved from storage into memory much more easily than the MP3 recordings themselves. These clearly constitute the bulk of the volume of the database, but can be relegated to the unstructured part of the database storage. Entity relationship databases can be used to represent linked knowledge in any domain. The richer the relationships, the more questions can be answered by such databases. As mentioned earlier, to be able to answer the sort of questions that we tend to ask from search engines, even they need to discover structure among the unstructured ocean of web data. Google discovers such structure using the so-called PageRank algorithm that they themselves invented. This algorithm gives each of the billions of web pages a PageRank value for each possible search keyword. To understand the basic principle of this, imagine that n different pages on the web contain a particular keyword W that someone may be interested in. If a single page on the web contained that keyword W, then clearly that page would be the best source of information on W. It would thus get the best possible PageRank of 100%. When Google crawls the web and discovers that in fact n different pages contain W, it initially assumes that what they each say about W is equally good or equally bad. Thus it divides their PageRank value with respect to W into n shares of 1 over n for each of the n pages. But then it recursively reevaluates and adjusts the PageRank of each of the n pages by counting the number and relative quality of the web links leading to each page from each of the other n-1 pages. The quality of a web link is equal to the PageRank of the origin page containing it, divided by the number of other links contained in that same origin page. In other words, if an origin page containing W provides only one single link to another page containing W, then that origin page must know something about the destination as a good reference about W, and its outgoing link inherits the entire PageRank of that page. On the other hand, if an origin page containing W provides 10,000 different links to 10,000 other pages, then that origin page may be a mere dump pointing to 10,000 things totally unrelated to W, in which case it is itself no particular reference for W, and the links originating from it are not particularly relevant to W, so they all get only 1/10,000th of their origin page rank. Very quickly, dump-style origin pages start losing PageRank, while a destination page P that is a good reference for W starts gaining PageRank, because every origin page pointing to it contains W and provides very few links to other destinations. So they must know that destination page P is a good reference about W. When you query Google, it responds with lists of pages linked in their page order rank. In practice, the real PageRank algorithm is much more complex, but its basic principle is exactly as discussed here. This being said, human knowledge is enormous, and the portion of it landing online is growing by a factor of 4 every year. PageRank, or the best database in the world, will never be able to capture precisely all possible relationships and inferences, especially as most of the data we generate is unstructured and exhaustively indexing it and structuring them is impossible. In spite of the PageRank algorithm, Google or Facebook or any other popular site or search engine could still not retrieve all the facts and details about a song or a movie of which one would only know a few words, notes, or images. Answering such queries would require that Google and many other sites organize their structural catalogs to be able to identify a song's lyrics based on a few given words, which Google can do today, a song's score based on a few given notes, which some websites are starting to be able to do today, a movie based on a few given images or descriptions of images, which is much harder to do, and then Google and company would still have to retrieve the author, composer, interpreter, producer, and other attributes of the song or movie. This can be easily done through secondary websites if they have put such information online. However, Google or Facebook do not provide such information themselves. They can just look for specific keywords. They are not designed to answer natural language questions such as what are the title, lyrics, score, video, date of a cartoon of a mouse performing magic. Google and others are working hard at such problems. This problem is at the core of what is called the big data challenge, to find a needle in a haystack or a gem in today's data ocean of several zettabytes. For your information, a zettabyte is equal to 10 to the 21 bytes, or otherwise 1,000 billions of bytes. Along that path, in 2011, the IBM Watson supercomputer beat the two world champions at the American TV game of Jeopardy! That knowledge game dates back to the 60s and went through more than 6,000 episodes. It is particularly hard as it challenges players to state questions matching given answers rather than the other usual way around. This slide shows the sort of question that Jeopardy challenges players with. After 3 rounds, Watson was first to reach the 1 million target, which IBM donated to charities, beating Ken Jennings, who had enjoyed the longest winning streak in Jeopardy's history, and Brad Rutter, who had grossed the highest gains of all Jeopardy times. You are warmly encouraged to click on the link of this slide to watch a real-time YouTube video underlying the speed with which Watson is able to respond to the challenges. While playing, Watson contained 200 million web pages of information, including all of Wikipedia, for a total of 4 terabytes of storage. It was, however, not connected to the web or to Google in real time. In fact, Google would have correctly answered 79% of the questions while missing the other 21%. More importantly, only 56% of the questions would have been on Google's top 10 results page. Another 23% would have been on the first 10 pages, the first 100 results of Google responses, but the missing 21% would not even have made it to the top 100 results. This goes to show that for all its power, Google's PageRank algorithm is not yet the answer to all of the world's questions.